Welcome back, ladies and gentlemen. We are continuing our vector discussion, and today we are going to focus on the concept of scalars and just some overall vector operations. Now, let's first and foremost kind of recap what we've discussed so far. Remember, a vector is something that has magnitude and direction. And if you now remember, we talked about magnitude was size or length or however you want to really think about it. Now, in this video, we are going to define what a scalar is. In all reality, a scalar is a real number. Kind of that's it, all right? Now, more specifically, we have to understand that a scalar of a specific quantity has magnitude, but it does not have direction. I want you to kind of think of it this way. Let's say that you were asking me for directions. We were walking around New York City, and you said, how do I get to the closest deli? And all I said was, go 4 blocks. That's it. I didn't tell you what direction to go or anything. I just said go 4 blocks. That's kind of what a scalar is. It's that 4. It's the size, it's the length, but it didn't tell me where to go. So what are we going to use scalars for? Well, we really use it for the idea of scalar multiplication. But before we get there, let's talk about vector operations. So remember, for an operation, what I mean is like addition, subtraction, division, multiplication, things like that. So I want to go ahead and discuss here our concept of vector operations. I'm going to start with vector addition. So if we have our 2 vectors, we're going to call them u and v in this example here. I can go ahead and simply add these 2 vectors together. We can call them a sum, or they also will call it a resultant after doing this operation. And so simply put, to add 2 vectors together is just adding the 2 x and y respective components of each of those vectors. So remember, the u sub 1 is that x component, right, of that vector. U sub 2 is the y component of that vector. V sub 1 is the x component of that vector. And v sub 2 is the y component of that vector. So if that's the case, to add these 2 together, all I have to do is simply add the 2 x's and add the 2 y's together. So I'm going to scroll on down, and let's go ahead and look at example 3 for a real basic vector operation example here in part A. So for part A, I want to add vectors u plus v together. In order to do so, I'm going to simply take their 2 components, and I want to represent them as they are, because this is what their vectors are. This is vector u, -1, 3. And I'm going to add that to vector v, which is 4, 7. And so respectively, I'm going to add their 2 vectors, -1 plus 4 and 3 plus 7 to get 3, 10. So that means that u plus v is the vector 3, 10. Okay. Now, let me just real quick kind of show you real fast of what vector addition looks like from a geometric perspective. Okay, just from a geometric perspective. We see this in 2 different ways, okay? We can take the sum of these vectors and represent them using arrows in a geometric kind of shape, I guess, if you will. Because ultimately, we have 2 ways of representing this. The tail-to-head representation and the parallelogram representation. The tail-to-head just simply means that if we would assume that one of our vectors starts, for example, at the origin, like u does right here, and if I were to make another vector from the terminal point of u, I could find the sum of those 2 vectors, right, by kind of going the tail of one to the head of the other, okay? Now that's if we go ahead and assume that this is one representation of it. The second representation that we can kind of look at with these 2 vectors is, well, what if they maybe have the exact same starting point, initial point, right? Let's say they both start at the origin in this case here. Well, obviously, I can't go a tail of one and ahead of the other like I did for that guy. So instead, what we can kind of always show, if you will, is we can make a vector u plus v, and it almost kind of shows this representation in this parallelogram form. So now I can kind of take the heads of all three of these vectors and combine them. And as you can see here, this does form a parallelogram representation there, okay? And again, they are just representations of how to show the vector addition. Now let's go back and talk about scalar multiplication. Scalar multiplication is simply taking that scalar or real number, right, magnitude, size, length, not direction, right, and multiplying it by a vector. All right, so let's take a look here. As you look what's going on here, k is going to represent my scalars. K is a real number. So if I'm taking k times some vector, it's almost like a distribution into that vector. Let's take a look at our example here. So let's go to part B, and let's do our scalar multiplication. So 3u is 3 times the vector u. So 3 times -1, 3 is going to simply just be -3, +9. That is it. So 3u would be -3, +9. Now, what if we kind of combined some operations, as we see here, in 2u plus -1v? Well, it's kind of our same order of operations as we would if we were doing things in PEMDAS. We would go ahead and say 2 times -1, 3 plus a -1 times 4, 7. So then we would have a 2 times -1, which is a -2. 2 times 3 is 6. Plus -4, -7. And at this point, we are going to go ahead and add those two vectors together. So we get -2 plus a -4, which is just subtraction to get us -6. And 6 minus 7 is a -1. So in this video, we went ahead and talked about scalars. We discussed their operations in terms of adding and subtracting vectors. We talked about scalar multiplication, and then we also kind of showed how we can maybe show a geometric representation of a vector addition.